One of the oldest types of nav aid still in use today is called the non-directional radio beacon, or NDB. While NDBs are not as common in the United States as they used to be, they are still used in other countries around the world. An NDB is simply just a ground-based AM radio transmitter that transmits radio waves in all directions. In the United States, these NDBs operate on the frequency range of 190 to 535 kilohertz. Because NDBs operate in this low to medium frequency band, they are not subjected to the line-of-sight limitations of space waves. To navigate via NDBs, pilots need to have installed in their aircraft an automatic direction finder, or ADF. The face of an ADF contains a needle that points to the relative bearing of the NDB. The relative bearing is the number of degrees measured clockwise between the aircraft's heading and the direction from which the bearing is taken from. You can use this simple formula to calculate the magnetic bearing to the station. Magnetic heading plus relative bearing equals magnetic bearing. For example, if your airplane is flying a heading of 030 and the ADF is indicating a relative bearing of 120, then that means that the NDB is at a relative bearing of 150 degrees. If you wanted to fly towards the NDB, 150 would be the initial heading to turn to. When flying directly toward the NDB, the needle will look like this, pointed straight up at the NDB station. Once crossing over it, the needle will reverse direction, but still point at the NDB as you fly away from it. It is possible to track both towards and away from an NDB station. This sounds really easy, right? Just keep the needle straight up and you'll fly right towards the station. Well, in a no-wind situation, that would probably be just fine. However, most of the time there is, in fact, wind. If a pilot were to keep the needle straight up on a windy day as they were navigating, they'd be doing a procedure called homing. Homing is not a recommended procedure to follow, as you would not be flying in a straight line. Instead of homing, tracking should be used to fly from station to station in a straight line. Tracking involves compensating for the wind by turning slightly into the wind and thereby staying on course. When you are on course and tracking to the station, the airplane's wind correction angle should equal the number of degrees the ADF is deflected from straight up. NDBs can be spotted on sectional charts with this magenta-colored symbol. In the vicinity of the symbol, you will find a box containing the name of the NDB, frequency, ID, and associated Morse code. Before you can actually navigate via an NDB, you need to tune and identify the desired station. Tuning in a station is pretty easy. Just look up the frequency on your chart and enter it into your receiver. After it's entered, we need to confirm that we are receiving the correct station and that it is operational. As part of an NDB's transmission, they'll send out their ID in Morse code format. We, the pilots, must listen to the Morse code and verify that it matches what's printed on our chart. After we've identified the station, we can use it for navigation. However, since there is no flag on the instrument to advise us whether or not it is operating properly, we must continue to monitor the Morse code for as long as we intend on using the station. Luckily, we can turn down the volume so it's not as obnoxious. There are 4 different classes of NDBs. They all operate on the same principles, but the different classes contrast in how far away their signal can be reached. The weakest of all NDBs is the compass locator. This low-powered NDB uses less than 25 watts of power, giving it a range of only 15 nautical miles. The other 3 classes are labeled as medium-high, high, and high-high, with each offering progressively larger ranges. To receive a signal from an NDB, the aircraft's ADF is able to determine the relative bearing from the aircraft to the NDB station. This is accomplished through the use of 2 antennas on board the aircraft, one being the loop antenna, the other being the sense antenna. The loop antenna is a directional antenna containing 2 or more stationary loops of wire. Looking at just one loop, if radio waves hit the loop in any direction other than directly perpendicular, a voltage will be induced over the antenna. By using multiple loops, oriented in different headings, the system can deduce down to 2 possible headings that the signal is coming from, both 180 degrees apart. To remove this ambiguity, the sense antenna is also used. This antenna, which is more or less just a straight wire, looks at the electrical field of the signal, receiving an identical signal from all directions. Looking at the phase of the signal and not the amplitude, the ADF receiver compares the sense antenna signal with the loop antenna and is able to remove the ambiguity and deduce the relative bearing of the NDB station. Now, before you start relying on NDBs for navigation, you should be aware of its limitations. The first of many errors is called the thunderstorm effect. During a thunderstorm, the ADF needle will be temporarily deflected towards the lightning strikes instead of the NDB. Next is the night effect, where NDB signals can be refracted by the ionosphere and return as sky waves. This effect is largest during the dawn and dusk hours. This can cause interference with distant NDB stations. Mountains can also have an effect on the NDB signal as they can reflect the NDB signal. Finally, there's the coastal effect. As the airplane is flying across a coastline, the ADF needle will bend slightly towards the coastline when crossing it at an angle. All of these errors result in erroneous bearing information which affects the ADF needle. Since the pilot has to monitor the NDB Morse code, hearing any static on that frequency, along with the ADF needle acting erratically, are two indicators that there may be an error in what you are receiving.